Welcome back. In the last session, we had seen the fixed bias circuit, and I explained the limitation of fixed bias circuit. The limitation of fixed bias circuit is it doesn't have Q point stability. If temperature changes, if IC is changing, then Q point is moving. Then I explained the reason for it. The reason for changing IC is nothing but IC naught and IB and beta, all three parameters are depending on temperature. Then if temperature changes, your IC is changing, Q point is changing. Okay. Then I told that I don't want to go ahead with this circuit because it needs two power supplies. Then what to do? Instead of VBB, I can choose directly instead of VBB, I can choose VCC and then RB. Then whatever IB you want, that you can choose by RB only. Let us say your VCC is fixed, right? Then if VCC, because power supply is always fixed, if power supply is fixed, then whatever IB you want, then tell me what is your input KVL in this equation, in this circuit. Input KVL is nothing but IB is equal to VCC minus VBE divided by RB. So for now, instead of VBB earlier, it was VBB, now it is VCC, right? Then you can choose RB such that whatever IB you want, you can get it. And transistor is same, both are having same IB. Then you know what is, sorry, this is IC. Therefore, you know what is IC with respect to IB from the DC equation. IC is equal to beta into IB plus 1 plus beta into IC naught. Approximately you can ignore that IC naught and then you can say IC is equal to beta into IB. Just that is for approximation, but if you take exact equation, IC is equal to beta into IB plus 1 plus beta into IC naught, then the drop across RC, then you are getting VCE. Then this is what you have chosen. Then you thought you got operative point and you released, but the Q point is not stable because of temperature. Then I told that we want negative feedback. Therefore, the negative feedback is trying to compensate the change in IC due to temperature. Therefore, your Q point will be stable. That is what we are looking for. Okay. Therefore, this is what is your practical fixed bias circuit using single power supply. Okay. Remember, both are same only, right? Instead of VBB, now it is VCC. Then instead of having VCC here, the same VCC we are getting from here. Therefore, that is what is connected. But here, if VBB is 5 volt, let us say VCC 10 volts, then RB, if you say here 50K, here it will be 100K. Because we have to choose RB such that your IB should not be changed. KVL by KVL, and then by having the required value of IB, we can do it. Okay. Write down. I don't know, in the last session, if you are able to draw the circuit, fixed bias circuit, which is practical, fine. Else, you take it now and then represent that this is what is your IB. Whatever you want, we can get it. Right? Take it. But it doesn't have any negative feedback. Now we need to incorporate negative feedback such that we can compensate the change in IC due to temperature. Done? Okay. Write down second circuit. See, when you incorporate negative feedback, there are different feedbacks, but we can get negative feedback ultimately. Therefore, that is what is called self-bias or automatic bias or variable bias, but we cannot give the same name for two different circuits because we have two different circuits with negative feedback. But we cannot give same name, both are self-bias circuits, but here based on the geometry or connection or feedback, people are naming the second circuit. The third circuit name is self-bias circuit, but remember the second circuit what I am going to give now is also self-bias, both are self-bias, they are doing the bias on their own to control your IC or to control operating point, but we cannot give the same name, that's why the second circuit name is different. Now the second circuit name is collector to base bias circuit. Based on the feedback structure, collector to base bias circuit. It is not fixed bias, it is collector to base bias circuit. Okay, listen, don't write anything. If you take earlier, what is fixed bias circuit? Practical fixed bias circuit we have like this. Now collector to base, this is what is your feedback, okay, and this is RB. But how it is acting as a feedback and then controlling operative point, I will explain. Okay, and this is what is our base, and this is collector, and this is emitter. Listen, okay. Now let us say VCE is greater than 0.2, VBE greater than or equal to 0.7. To get those things, we have chosen RB, RC such that we are getting those things. Transistor is kept in active region, but whatever voltage, output current, that is what is Q point, that should be stable. Yes, because of this configuration it is stable, but how it is stable, I am explaining. Just listen. Tell me the current which is entering into base. What is that current? That is nothing but IB. Tell me the current which is entering into collector. That is IC. And this is what is VCE. Tell me what is the current which is what is flowing through RC. KCL. Tell me. The current which is what is flowing through RCL is nothing but this current plus this current. We know the current which is entering into collector is nothing but IC. We know the current which is entering into RB is nothing but IB. Therefore, what is the current which is what is flowing through RC? The current which is what is flowing through RC is nothing but IB plus IC. This is what is the current, right? Therefore, that is nothing but IB plus IC. Out of it, IB is going through the base and IC is going through this. Then this is nothing but IC to IB, and this is what is the current. Okay. Now listen. Qualitatively, I am explaining. The same thing I will give it to you through flow chart. Therefore, you will understand how the Q point is stable. Now, therefore, what is your Q point? Q point is defined as which is nothing but VCE, capital VCE, comma capital IC. This is what your Q point. Okay. Now tell me, if temperature increases, what will happen? Your IC will increase. Why? Because we know that IC is equal to beta into IB plus 1 plus beta into IC naught, and IC is function of reverse saturation current IC naught, input base current IB, and beta. All three in turn depend on temperature. This is what we had seen. Therefore, if temperature increases, IC naught is increasing, IB is increasing, beta is increasing, your IC is increasing. When IC is increasing, now listen, when IC is increasing, definitely the current which is what is flowing through RC is also increasing, because IB plus IC, if IC is increasing because of temperature, IB plus IC is also increasing, the drop across RC is increasing. Then if you write output KVL is equal to this voltage, VCC is equal to this voltage plus this voltage, then the drop across RC is increasing because of increase in IC because of temperature, then your VCE will decrease. When VCE is decreasing, the same VCE is applied to your input. That is what is called self-bias. Therefore, the voltage whatever you are getting, that itself is biasing your input voltage, right? If there is any change in output voltage which is VCE, that will be sampled and then fed back, and then that is itself is feedback, that itself will control. How? Therefore, when VCE is decreasing, then definitely your VBE will decrease, because that VCE is equal to the drop across RB plus VBE, right? When VCE decreases, definitely your VBE will decrease. Definitely the VBE will decrease, because this is what is your VBE. When VBE decreases, surely IB will decrease. When IB is decreasing, your IC will decrease. Therefore, what I am saying, let us say this is what is my IC, right? Due to temperature, IC is increasing. When IC is increasing, because of negative feedback, again it is coming back, then it is making IC constant. I am repeating once again. If temperature increases, IC increases. When IC increases, IB plus IC increases, then the drop across RC increases, then VCE decreases, then VBE decreases, then IB decreases, then IC decreases. If there is any change or if there is any increment in IC, but because of temperature, that IC is coming back. Because of negative feedback, the IC is coming back and then making IC constant. This we don't have in the case of fixed bias circuit because your bias is fixed. Because earlier this RB is connected to VCC, which is fixed, but now it is connected to VCE, that is not fixed. If VCE changes, which we are supposed to have constant voltage, if VCE changes, then definitely VBE changes, then IB changes, then IC changes. Therefore, it is trying to correct your Q point. Therefore, we are going to get Q point stability. Okay. But now, let me explain the same thing using flowchart. Now, if temperature increases, then don't write, just listen here. Your IC naught increases, your IB will increase, your beta also increases. Because of all three, IC is increasing. When IC is increasing, just listen. What about IC plus IB? Whatever I explain, I am explaining through flowchart. IC plus IB also increases. When IC plus IB is increasing, then what about the drop across? Therefore, IB plus IC into RC. This is increasing. When this is what is increasing, then what about your VCE? VCE decreases. Because when the drop across RC is increasing, your VCE will decrease because this voltage is constant. When VCE decreases, then what about IB? IB decreases. If IB is decreasing, because why IB is decreasing? Because VBE is decreasing. VBE decreases. When VBE is decreasing, IB decreases. When IB is decreasing, then your IC decreases. Therefore, if you ask me, overall, what is your IC? Your IC is almost constant. Therefore, due to temperature, there is an effect in IC, but because of negative feedback, there is a decrement in IC or there is a compensation in IC. Overall, your IC is almost constant. Okay. Now take the circuit and then take the flowchart. The same thing we can go ahead for using mathematical analysis. Then I am going to define stability factors, because how much is the negative feedback, that is what is going to control IC. That part I will explain. You can take it. Okay. If you observe clearly, I didn't write it like IC is absolutely constant. I am saying it is almost constant. That depends on negative feedback. Okay? What does it mean? Let us say due to temperature, your IC is increasing by some 100 microampere. Due to temperature, your IC is increasing by 100 microampere. Then because of feedback, if 100 microampere is decreased, whatever IC which is increased due to temperature, if the same amount of current is decreased because of negative feedback, perfect, then IC is absolutely constant. But what is the guarantee that IC is increasing by 100 microampere, then because of negative feedback, let us say it is decreasing by only 80 microampere, then still effectively there is a 20 microampere increment. Therefore, your negative feedback is not perfectly compensating the change in IC, but at least it is compensating. It is very better than your fixed bias circuit where there is no compensation due to temperature. You got it? Further, qualitatively I can explain that if temperature increases, IC increases. Then because of negative feedback, IC decreases. But how much it is increasing, how much it is decreasing, and then overall what is your IC, that I cannot explain qualitatively. For that we need mathematical analysis or quantitative analysis, right? That's why people define something called stability factor or stability factors. Okay? Write down. Stability factors. Write down subheading stability factors. In this session I can complete collector to base bias circuit, means including mathematical analysis or defining stability factor or deriving stability factor. Then maybe next session we can see self bias circuit with a different feedback in the sense negative feedback only, but with a different connection, then we will get negative feedback. That part we will see. Okay. Remember, you can call this circuit also self bias circuit. The bias, the VBE is biasing on its own, right, and controlling your IC, but not completely. And one more point I want to explain, which is very important, not only here, everywhere, wherever negative feedback is there, you can take this concept. How did I explain? If you take the flow chart, how did I explain? If temperature increases, IC naught increases, IB increases, theta increases, IC increases. Then because of negative feedback, your IC is decreasing. Then I told IC is almost constant. Practically it will not happen like that. But how I explain? Sequential manner. Sequential manner means I am expecting IC to be something. But because of temperature, IC is increased. Now because of feedback, it is controlled back. Therefore, if you see the explanation is like IC is increasing because of temperature and IC is coming back due to negative feedback. Therefore, IC is ultimately constant. Under steady state, it is constant. Therefore, but in between there is a transition, increment and then decrement. But that is not true practically. That is for our understanding purpose. Practically what is true? Let me give you a small analogy to understand. Okay? I am the person, right? But because of my internal energy or because of my internal thoughts, I want to move. Definitely everybody wants to move. Then I am trying to move. But according to you, you want me to stay exactly at this point. If you want me to stay exactly at this point, then, but you cannot control me, then I am moving. Therefore, according to you, I am not stable. I am not standing exactly at a given point. Then what to do? If you want me to make me stable, then take iron chain, then wind me with iron chain and with 4 angles, 1, 2, 3, 4, pull it and then hook it to walls, let us say, then imagine. Am I stable now? What does it mean? If I want to go, I am able to move, but the explanation what I gave is something like this. I want to move because of my internal energy. I am just taking one step. But because of the chain which is what is pulling me, I am going back. Ultimately my position is stable. I am stable, and because of what? Because of the chains. Those chains are nothing but negative feedback which is not allowing to do not see any change in the position of my body. That is what your intention, let us say. Is that what happening practically? No, but the explanation what I gave is in that way. I want to move. I am moving because of my internal thoughts, but because of the chain, I am going back. Ultimately my position is stable, but remember, that is not the practical scenario. The practical scenario is this. I want to move. When I want to move, immediately the negative feedback or the chains are coming into picture such that I'll be here only. I'm trying to move, immediately at the same time negative feedback is coming into picture which is not allowing me to move. That is what is very important. Therefore, it is not that I am moving and then because of the change I am going back. It is not spring to see this effect. Therefore, this is what is iron chain, hard coded chain. Therefore, if I want to move, immediately the negative feedback is coming to picture and it is trying to compensate. That is what is happening. Your IC is trying to increase. The moment it is trying to increase, negative feedback will come into picture. It will not allow the change in IC. It's not that IC will increase and then it will come back. But if I don't explain like a sequential manner, we will not understand. Remember, this is for our understanding purpose. Practically, IC will increase and the negative feedback will come and then make it constant. No, that will not happen. Practically, the moment IC is trying to increase, immediately negative feedback will come into picture and it will not allow the change in IC. That is what is ideally expected. Ideally, IC to be absolutely constant, but whether it is constant or not, for that we need mathematical analysis. That is what we are going for. Hope this is clear, right? Now, write down stability factors, okay? Let's see that. Now let us say I am expecting my IC to be 1 milliampere. This is what is my expectation, or I am trying to keep my IC at 1 milliampere. But let us say due to temperature the IC is increased. Let us say the new IC due to temperature, IC is becoming 1.1 milliampere due to temperature. Therefore, tell me, due to temperature change, okay, due to delta T, what is delta IC? Delta IC, let us say this is 100 microampere. Therefore, what is delta IC? 100 microampere. That is due to temperature. Now there is a negative feedback, right? Due to negative feedback, let us say this is what is compensated to a new value. Let us say this is what is our IC dash, where it is 1.02 milliampere. But this is what is. Therefore, now tell me what is change in IC. Here the change in IC, let us say minus 80 microampere. The meaning of minus is nothing but it is decreasing. Due to what? Due to negative feedback. Right? Therefore, I am expecting IC to be equal to 1 milliampere, but because of temperature there is an increment of 100 microampere. But again, sequential explanation, okay? Then because of negative feedback, there is a decrement of IC, which is means your negative feedback is controlling 80 microampere out of 100 microampere, but still there is a change in IC that is around 20 microampere. Therefore, if you ask me, still there is a change in IC. Delta IC, which is equal to 20 microampere. That is due to what? Ultimately temperature, right? Directly 100 micro, but because of negative feedback something is compensated, but overall still there is a change in 20 microampere, right? It is not absolutely compensated, right? Whether it is absolutely compensated or not, for that we should know the mathematical analysis and then we need to calculate. Qualitatively we cannot explain, we cannot do that analysis. Now let us say out of 20 microampere, right? Let us say out of 20 microampere, here I don't have space, out of 20 microampere, let us say the change in IC, that is 20 microampere. Out of 20 microampere change, right? We know that your IC, right? IC is equal to beta into IB plus 1 plus beta into IC naught. Then this is nothing but function of IC naught, IB and beta, right? Now out of change in 20 microampere, therefore ultimately now what is change in IC? 20 microampere. Then out of 20 microampere, IC naught will have some job, IB also will have some job, beta is also having some job to have the 20 microampere. Therefore the change in IC naught, let us say IC naught is affecting IC, IB is also affecting IC, beta is also affecting IC. Let us say out of 20 microampere, 18 microampere is due to IC naught, and let us say 1 microampere is due to your IB or VBE, then one more 1 microampere that is due to beta. Practically people found from mathematical analysis as well as practical analysis or practical experiment, practical experiment it is difficult to find. From mathematical analysis, that's 20 microampere whatever we have, the majority of the change, remember don't take these values as granted, these values for your understanding purpose, okay. Now out of 20 microampere change in IC, majority of the current change is due to IC naught only. Therefore majority of the current IC change is due to IC naught only. Because of IB beta there is a change, but the change can be neglected with respect to the effect of IC naught. That is what people explained, that is what we got from mathematical analysis. Therefore IC naught is very important. That's why maybe if you speak about stability factor S is defined as what is the change in IC, because there are three independent parameters, one dependent parameter, that's a partial differentiation. What is the change in IC? Because of what? Because of only IC naught. Because of only IC naught, okay. When IB comma, IB means VBE, VBE is nothing but V gamma, VBE comma, because this IB is nothing but your VBE, your IB is affected because of VBE, right. If VBE decreases, your IB will increase, right. Therefore when VBE and beta they are constant. Now S dash is defined as what is change in IC due to change in VBE, V gamma basically, when IC naught comma beta they are kept constant, they kept constant. Now S double dash is nothing but the change in IC due to change in beta, when IC naught comma VBE they kept constant. But out of all three, this is what is significant, that's what I told, right. Therefore IC by IC naught, the change in IC due to IC naught, in this example that is 18 microampere, the change in IC due to IC naught, okay. But here it is ratio, therefore it will have no unit, therefore S is nothing but simply ratio, therefore majority of the change in current is due to IC naught only, okay, practically. But can anyone tell the ideal values of stability factor? Can anyone tell the ideal values of stability factors? What are we expecting ideally? Ideally I want IC to be constant. Ideally I want IC to be constant irrespective of temperature. If I want IC to be constant irrespective of anything, then can anyone tell what should be the minimum value or what should be the ideal value of S? What should be the ideal value? Qualitatively we can say I want IC to be constant irrespective of anything. Then what should be the S value? 1. Let us say if you say 1, then what is change in IC? Change in IC naught. Whatever change in IC naught you have, the same thing you will get in the IC. I don't want to see the change in IC because of anything. Therefore ideal value should be 0. For example, when I say S is 0, what does it mean? The change in IC is 0 or IC is constant. When IC is constant, what is the change in IC? Your IC is not changing because of any reason. Therefore all stability factor should be 0. Ideally we are expecting stability factor to be equal to 0. But let's solve what is the stability factor for the circuit. Then only S is important. S dash, S double dash, that is not important. But if you want, you can do it for your knowledge purpose. The procedure, I'll give you the, we will solve that in the classroom. Therefore, how to solve this S the same way, you have to solve S dash and then S double dash. That is what your homework. Simple, we need to differentiate IC naught. If you want to get S dash, we have to differentiate with respect to VB and then keeping other things constant. Okay. We are going to solve for this and then let's see what are we getting. Practically, what are we expecting? Minimum value. Ideally, what are we expecting? 0. But let's see whether we are getting 0 or not based on the mathematical analysis. Okay, take it. Then let's apply by input KVL, output KVL, devise the equation. We can do whatever you want. Remember, ultimately, if the problem is related to DC analysis, only these three things: either input KVL or output KVL or both. That's it. Along with the devise the equation. There is nothing to if you want to analyze anything. But we need to have the definitions. Then based on then consider input KVL, output KVL, devise the equation. Then you do manipulation whatever you want. Finally, whatever you want to calculate, we can calculate. Take these values. I'll give you 2 more minutes to write all these things. Okay. Already circuit is drawn before only, right? Only you have to take this. This is example only, just to explain. Okay. Means your change in IC is still there, even though negative feedback is there. Because negative feedback is not 100% compensating your change in IC. If it is compensating change in IC 100%, your stability factor will be 0, S dash will be 0, S double dash will be 0, everything will be 0. But practically it is not. Why it is not? We will see from mathematical analysis. Okay. Over. Now let's see. I think it will take only 10 to 15 minutes. I think within this session we can complete the stability factor derivation. Okay. Now this is what is the definition, right? Let me arrange everything. I need space. Therefore, I will use this also completely. Okay. The same thing we need to do for next circuit. Okay. Tell me what is your output KVL? Remember, very simple. Now I want to get IC and then differentiate that IC to get stability factor. Now to get IC, we want output KVL. Therefore, what is output KVL? VCC is equal to the drop across RC, which is nothing but IB plus IC into RC plus VCE. This is what is equation 1. Then what is input KVL? Input KVL. Input KVL is nothing but the same VCE is fed back at the input. Therefore, VCE is equal to drop across RB. What is drop across RB? IB into RB plus VBE. This is equation 2. Combine 1 and 2. Therefore 1 implies VCC is equal to IB plus IC into RC plus VC is nothing but IB into RB plus VBE. Right? Now, can you take IB common? If you take IB common, then you will get RB plus RC, RB plus RC plus IC into RC plus VBE. Right? Just listen. I'll give you time. Therefore, this is what your VCC. Actually, from this equation also I can explain the compensation. Your VCC is constant, right? Then your VB is almost constant. There is a change, but the change is not significantly changing your VCC. Sorry, that's the complete term. If there is any reason where IC is increasing, then IB has to decrease to make this equation to a constant value of VCC, right? Mathematically also we can say, due to any reason if IC is increasing, IB should decrease. When IB decreases, IC will decrease. Ultimately, IC, IB constant. That is nothing but compensation. Okay? Now, this is what is the equation which we need to differentiate. I want to differentiate IC with respect to IC naught. But where is IC naught in this? I don't want to see IB also. I want to write IB in terms of IC. And we know that IC is equal to beta into IB 1 plus beta into IC naught. I derived this already, right? That's why I derived, because majority of the time for DC analysis we always use this equation. Okay? Now tell me what your IB. Therefore, IB is equal to IC minus 1 plus beta into IC naught divided by beta. That you substitute in equation 3. Therefore, 3 implies VCC is equal to, what is IB? IC minus 1 plus beta into IC naught divided by beta into RB plus RC. RB plus RC plus IC into RC plus VBE. Right? Now, listen. Can I differentiate? Everywhere IC is there, IC naught beta only, right? What is differentiation of VCC with respect to? And we know that. What do you want to find? We want to find, we need S is equal to change in IC due to IC naught when VBE comma beta constant, right? Keep VBE beta constant and differentiate IC with respect to IC naught. That is what your stability factor is. That is what we need to find. Okay? Therefore, just listen. What is differentiation of VCC with respect to IC naught? 0, because this is constant. Differentiation of IC with respect to IC naught? Yes. Minus differentiation of this. IC naught constant, 1 plus beta is constant, right? For 1 plus beta and IC naught is not constant. This is differentiation of IC naught with respect to IC naught 1 only. 1 plus beta by beta into RB plus RC plus differentiation of IC with respect to IC naught S into RC plus differentiation of VBE with respect to IC naught, because we have to take VBE constant 0, right? Then you take it, then differentiate, then tell me what is your stability factor. You differentiate this equation IC with respect to IC naught and then tell me what is your S value. That is homework for you. We have 7 more minutes for this session. Out of 7 minutes you can take 2 minutes to write, and the remaining 5 minutes you can invest to derive the stability factor. Okay? Try to take these equations and derive, and then tell me what is stability factor. Okay? I will not derive. You have to derive. This is simply mathematical analysis, right? And we want to know what is the stability factor here. One more minute. Remember, if IC is constant, then VC is also constant. Therefore, if you are able to keep IC constant, then your operating point is constant. Therefore, this is what is Q point stability. We are able to achieve Q point stability using feedback, that to negative feedback. Tell me what is S value. Is it over? I will give one more minute. Try to derive that. Let me give you the first equation. Just listen. Therefore, what is differentiation of VCC? 0. 0 is equal to, then differentiation of IC, that is what is stability factor, yes, minus differentiation of this IC naught, right? Therefore, differentiation of 1 plus beta and IC naught 1 plus beta only. Therefore, it is 1 plus beta divided by beta into RB plus RC plus differentiation of IC with respect to IC naught S only plus S into RC plus 0, right? Therefore, can you take S common? 0 is equal to, if you take S common, what you get? Here, what do you have? RB plus RC, right, by beta. Then if you take S common here, you will get RC. Then that minus sign, maybe you can take to right hand side. If you take it, then what you will get? You will get 1 plus beta by beta into RB plus RC. This is what you will get, right? Then you need to calculate RB. Therefore, if you take LCM, beta will be cancelled, then S will be RB plus, if you take RC common here, you will get RC into 1 plus beta is equal to 1 plus beta into RB plus RC. Therefore, what is stability factor? S is equal to 1 plus beta into RB plus RC divided by RB plus 1 plus beta into RC. This is what is our stability factor. Okay, take it. I'll stop now. Maybe for 2 minutes you can take that derivation and then you can put it in the box. Then let's see the observation of the stability factor. But are we getting 0? This is not 0. But ideally we are expecting it to be 0. Therefore practically it is not 0. That I already told you. It is not absolutely making negative feedback 100% to make IC constant. That's fine. You take it. Then the observation part I'll explain in the next session. Then in the next session the third one also will be closed. With that I can say DC analysis is over. Okay. Thank you.